All right, and for this last problem on the worksheet, we have question 8. It says, consider the function phi, which is equal to the natural log of r, where r here is the magnitude of the position vector vector r, which is just xi plus yj plus zk. So in other words, the scalar r here is just the root of x squared plus y squared plus z squared. Now, question A says, show that phi is a potential function for the radial field f, which is the position vector r divided by the square of its magnitude. So notice this does not satisfy the inverse square law. If I take the magnitude of this vector f, I'm going to get 1 over r, not 1 over r squared. Our job is to show, again, that phi is a potential function. So in other words, show that the gradient of phi is equal to this vector field f. All right, well, so to do that, first, just recall that if I differentiate this quantity r with respect to x, I get x over r, and then the y and z derivatives likewise are y over r and z over r respectively. Okay, I discussed this in quite a bit of detail back in section 15.5. So if I want to differentiate phi with respect to x, okay, I can go ahead and use the chain rule together with these facts right here. Okay, so the x derivative of phi will be 1 over r, because I'm differentiating a logarithm. And then I have to multiply by the derivative of what's inside. So I'm going to, in other words, differentiate r with respect to x. And what we just said right up here, right, is that the r, or the x derivative of r is just x over r. So we get that the x derivative of phi is x over r squared. And likewise, the y derivative of phi is y over r squared, and the z derivative of phi is z over r squared. And so the gradient of phi is equal to, well, the x derivative for the I component, the y derivative for the j component, and the z derivative for the k component. So we just put those all in, x over r squared, y over r squared, z over r squared. Well, that's just 1 over r squared times the vector x, y, z, which is this position vector r. So we get that the gradient of phi is equal to the position vector r divided by the square of its magnitude, and that's what we're calling this vector field f. So yeah, phi is a potential function for the radial field f. All right, now part B, it says compute the flux integral of this vector field f over the sphere of radius a centered at the origin. And we're orienting the sphere outward. And it says, note here that the divergence theorem does not apply. Why? Well, for the exact same reason it didn't apply in question 7, right? Our vector field f here, which is r over r squared, is not defined at the origin. And the region enclosed by the sphere, radius a, that contains the origin, right? So divergence theorem doesn't apply, but we can still compute the flux of the vector field over the sphere by just noting that, well, the normal vector, right? The unit normal vector pointing outward from the sphere, that's just the position vector r divided by its magnitude. So it's r divided by a, right? Because the magnitude of the position vector is just a, because we're on a sphere of radius a centered at the origin. So n is r over a, and the dot product then of f with n, this is going to be r uh, over r squared, right? And scalar r, again, is just the value a. It's just the radius of the sphere. So r over a squared dotted with r over a, that's going to be the magnitude of r squared over a cubed. And that's just a squared over a cubed, which is 1 over a. And so the flux of the vector field over this sphere of radius a centered at the origin is simply the surface integral of this constant 1 over a. And so this is 1 over a times the surface area of the sphere, and that's 1 over a times 4 pi a squared, and that simplifies to 4 pi a. All right, cool. So now let's go ahead and look at part C. Okay, part C says, all right, for epsilon greater than 0, let S sub epsilon denote the sphere of radius epsilon centered at the origin. Okay, so here's our S sub epsilon, and we're going to choose epsilon, so S sub epsilon will lie within S sub a, okay? And we're going to let D sub epsilon denote the solid that lies between these two spheres. Our job is to compute the triple integral of the divergence of the vector field f over this solid region d sub epsilon. And it says your answer will depend on epsilon. All right, well, to do that, we're going to go ahead first and compute the divergence of the vector field. And I actually already did this back in section 15.5, but just to remind you, if I take this vector field f in component form, it's just x over r squared, y over r squared, z over r squared. So to compute the divergence, I'm going to need the x derivative of the I component, the y derivative of the j component, and the z derivative of the k component. So the x derivative of the I component I can compute using the quotient rule together with the chain rule. All right, so I'm going to do low d high, so that's r squared times 1, minus high, which is x, times d low, that'd be 2r times the derivative of r with respect to x. And as I mentioned just a few moments ago, right, the x derivative of r is just x over r. And notice here these r's will cancel out, so I get r squared minus 2x squared up in the numerator, and I have an r to the fourth in the denominator. Now likewise, the y derivative of y over r squared, that's r squared minus 2y squared all over r to the fourth, and the z derivative of z over r squared, that's r squared minus 2z squared all over r to the fourth. And so the divergence of this vector field is the sum of these derivatives. So I get the sum of these expressions here. So now combining like terms, I'm going to get 3 of the r squareds, and then I'm going to factor out this 2. I have minus 2 times the quantity x squared plus y squared plus z squared, but that is r squared. So in fact, I have 3r squared minus 2r squared up in the numerator, which is just r squared. So r squared over r to the fourth is 1 over r squared. So that's the divergence of our field. Okay, so now to compute the triple integral of the divergence over the solid region d sub epsilon, I'm going to integrate 1 over r squared over this solid, right, that's bounded by these two spheres. So I'm going to use spherical coordinates to do this. Okay, this region d sub epsilon can be described in spherical coordinates as letting, well, the angle phi vary from 0 to pi. Theta, the polar angle, is going to vary from 0 to 2 pi. And then rho, which is just the radial distance from the origin, which is really just r here, okay, just a different label for that same quantity, just the radial distance from the origin. It's going to vary from, well, the radius of the inner sphere. So in other words, it's going to vary from epsilon out to the radius of the outer spheres up to a. So I get 1 over r squared, which again, this is really just rho here, just different label. So I have 1 over rho squared times, and don't forget the rho squared sine phi, that's just the coming from the volume element in spherical coordinates. And then I have d rho, d phi, d theta with the appropriate limits. Now notice the rho squareds cancel out. So when you split this up, you wind up getting 4 pi times the quantity a minus epsilon. All right, so now for part D, it says what happens to the value of your triple integral in part C as you let epsilon approach 0? Well, as we let epsilon approach 0, here, let me take this out. Notice that this quantity will approach just 4 pi a, right, because epsilon is going to 0. So let me take this out so it's less messy. So what we're seeing here, right, the integral that we took in part C, this triple integral of the divergence, we know from the divergence theorem for hollow regions that that's equal to the outward flux through this outer sphere, S sub A, minus the outward flux through this inner sphere, S sub epsilon. Okay. Now, we just found, right, in part C that this integral on the left, the triple integral, is 4 pi times the quantity a minus epsilon. And in part B, we computed the outward flux through the sphere of radius a, that was 4 pi a. And by the exact same argument, this outward flux across the blue sphere, that's 4 pi epsilon. So as we let epsilon approach 0, okay, I get 4 pi a on the left. And here, this is just equal to 4 pi a, but 4 pi epsilon is going to approach 0, right? So as we shrink this blue sphere to a point, right? So in other words, we shrink it down to the origin. Okay, this outward flux term is going to go to 0. 4 pi epsilon goes to 0, whereas um, uh, the outward flux across the sphere of radius a, of course, just depends only on a. All right, so in the end, of course, we get 4 pi a is equal to 4 pi a. Now, I will just finish by saying, this kind of thing is not always possible. Now, if we're avoiding the origin here because of this inner sphere S sub epsilon, and then taking a limit, we get convergence of these appropriate integrals. Now, there are vector fields. If I, for example, just change the exponent here on the magnitude r, I can do that in such a way that when I do this shrinking down process, this outward flux in fact blows up. There's actually a singularity at the origin, and so things don't work out quite in this way. But in any event, that is a good place to stop, and thank you so much. All right.